Welcome to The Explainer. Today, we're going to pull back the curtain on the invisible engine that runs, well, basically our entire digital world, the database. Every single time you click or search or like something, you're kicking off this fascinating high-speed chain of events. So what really happens behind the scenes? Let's find out.
It feels instantaneous, right? You hit enter and boom, there's your answer. But in that tiny fraction of a second, your one little click kicks off an absolutely incredible journey. We're going to follow that request right from your screen, deep into the brain of a database, and all the way back with an answer. And yeah, all in the blink of an eye.
So first things first, how does a machine even understand what a human is asking for? Before a database can go find your data, it has to translate your request into a language it actually gets. This is the critical first step. Figuring out the question and then mapping out the absolute smartest, fastest way to get you the answer. What you type gets instantly translated from something human-readable into the database's native tongue, which is called relational algebra. Now, you should think of it less like a language and more like pure logical math. It totally removes any ambiguity and gives the system a perfect, step-by-step blueprint of exactly what it needs to do.
But here's the cool part. Before it even starts, the database doesn't just blindly follow those instructions. It has this thing called a query optimizer that acts like a really sophisticated GPS. It'll analyze dozens, maybe even thousands of different paths or execution plans to find your data. It calculates the estimated cost of each path, in time and resources, and then it picks the absolute fastest route.
Okay, so the database has its GPS route all planned out. But the destination is one little piece of data in a massive digital library with billions of records. How on earth does it find it without reading every single page? Well, the secret is something you've actually used before, an index. Just like in the back of a book, but, infinitely more powerful.
Trying to do a brute force scan of every single record would take forever. So the system uses an index instead. It's a totally separate, much smaller, and perfectly sorted list. Now, it doesn't hold the data itself, just two things, the term you're searching for and a pointer, which is basically a digital address telling the system exactly where to go to find the full record.
And here's that shortcut in action. The system just scans the tiny, sorted index, gets the exact digital address, and then jumps straight to the data. It gets to completely bypass everything else. This one trick is what reduces the search time exponentially. It turns what could be a minutes-long ordeal into a millisecond operation.
But wait, how do you keep that index perfectly sorted when data is being added and removed millions of times a second? Well, databases use this incredibly clever structure called a B+ tree. Just try to imagine a perfectly balanced family tree where every leaf, or, every piece of data, is the exact same distance from the top. It is constantly reorganizing itself to stay balanced, which ensures searches are always lightning fast and predictable, no matter how huge the database gets.
All right, let's zoom out a bit and move to the physical level to see how this data is actually stored and, more importantly, kept safe. We're talking about the real hardware now, the memory and the disks where every single piece of information lives.
See, data doesn't all live in the same type of house. It's a hierarchy. You've got the super fast, super expensive penthouse suite, that's RAM, for data that's needed right now. Then you have the main apartments, your SSDs, for everyday storage. And finally, you have this deep, slow, but massive archive in the basement. That's tapes, for backups. The system is constantly moving data between these levels to perfectly balance speed, cost, and capacity. And to avoid constantly going to those slower disk drives, the system uses another clever trick, the database buffer. Think of it like a workbench. It's a chunk of that super fast RAM where the database keeps copies of the data it's using right now or uses all the time. This drastically cuts down on slow disk access and just keeps everything moving at full speed.
But what happens if a physical disk drive just dies? It happens. That's where technology called RAID comes in. It basically links a bunch of cheap disks together so they act like one super reliable unit. It might store an identical copy of your data on two separate disks, or it might cleverly spread pieces of your data across several disks in a way that lets it rebuild everything if one of them fails. Either way, if one drive goes down, zero data is lost.
So, the system is fetching and updating data at these incredible speeds. But with so much happening all at once, how does it prevent total chaos? Well, it follows a very, very strict set of rules to make sure every single operation is reliable, consistent, and totally secure.
Every critical operation, think transferring money or booking a flight, is wrapped in this digital bubble called a transaction. A transaction is basically an all-or-nothing promise. For a bank transfer, that means both debit from account A and credit to account B have to succeed. If either one of those steps fails for any reason, the entire transaction is just canceled, and the database acts like it never even happened. No money just vanishes into thin air.
This all-or-nothing promise is part of a bedrock principle for databases known as ACID. Atomicity is that all-or-nothing rule we just talked about. Consistency means the database's own rules are never broken. You can't overdraw an account, for instance. Isolation means that even with thousands of things happening at the same time, they don't trip over each other. And durability, well, that's the ultimate promise. Once the database says your change is saved, it's permanent, even if the power cuts out a second later.
And of course, protecting the data itself is paramount. This happens in layers. Authentication is the front door, asking, "Who are you?" Access control is like the keycard, deciding which rooms you can actually enter. Encryption is like writing all the data in a secret code, so it's totally useless if someone steals it. And auditing? That's the security camera system, logging every single action to track down anything suspicious.
Okay, so our single query is complete, the answer's been safely returned. That's great for one person, but how does this scale to serve millions of users all around the globe? And how do we unlock even deeper insights from all of that data?
Well, the solution is to stop relying on one single giant machine. With a distributed database, the data is strategically spread out across many computers, sometimes all over the world. This is the fundamental architecture that powers pretty much every massive global application you use today.
The benefits here are huge. A single, centralized database creates a bottleneck, right? It has one point of failure, and it can be super slow for users on the other side of the planet. But a distributed system is incredibly resilient. If one computer fails, the others just pick up the slack. It's faster for everyone because you're being served by a data center near you, and it can scale almost infinitely. You just add more machines to the network. And now, with all this data perfectly organized, stored, and accessible, we can do something truly powerful: data mining. This is the process of sifting through these massive data sets to discover hidden patterns, correlations, and insights that just weren't obvious before. We're talking about things like predicting customer behavior, detecting fraud, or identifying new market trends.
And that, right there, is the true power of the modern database. It's not just about answering the questions we already have. It's this silent, lightning-fast engine that organizes our world's information in a way that empowers us to discover answers to questions we never even thought to ask.